Hi, everybody. It's my pleasure to introduce Itay Hen, who's going to give us a talk about his research on Hamiltonian simulation. So, Itay, if you please, you can go.
Okay, thank you. Thank you for the introduction. Hi, my name is Itay Hen. I'm from the University of Southern California's Information Sciences Institute. And I'm really excited to tell you about this work about, I guess, a quantum algorithm, a novel quantum algorithm for simulating Hamiltonian dynamics. This is joint work with Amir Kalev, who is also at ISI. And while presumably, most of you know what Hamiltonian simulation is, I'll still spend, I guess, 1 or 2 minutes talking about that. So that's basically, Hamiltonian simulation is basically what you want to do when you want to learn about the time evolution of quantum many-body systems, but using a controllable system, not basically doing an experiment, because sometimes it's very difficult, but maybe you want to simulate it. And while, before the age of quantum computing, we used to do it on classical machines, classical computers, we know that it's this job of simulating the dynamics of quantum systems is very difficult to do classically, and therefore doing so on a quantum circuit really has been recognized as one of the most important uses for quantum computing going forward. And when I talk about Hamiltonian dynamics in this talk, I will assume that somebody gives us a Hamiltonian H and an initial state psi naught, and what they want to know is basically what is the state of the system psi t after evolution for time t. So this is basically if the Hamiltonian is assumed to be time independent, which we will assume it for this talk, but it's not necessary, generally speaking. Then what we want to know is basically how the action of e to the minus iht, the quantum time evolution operator, when it acts on psi 0, what is the quantum state that it gives us? And sometimes, the Hamiltonian could be something very physical, but the experiment is very difficult to carry out. So what we want to do is we want to simulate or write a circuit, in our case, a quantum circuit, or a sequence of gates that when it acts on an initial psi 0 initial state, it gives us at the end the state of the system after time t. So that's basically what we want to do. And of course, what we're interested in is figuring out a good algorithm to do that with a minimal or optimal computational complexity. And I guess if you look at the current state of the art, there's many multiple good algorithms, but I guess I'm choosing one that is by Berry et al. Normally what one would do, and this is not true for all the algorithms out there, but generally speaking, I'm generalizing, what one does normally is take the evolution operator and basically slices the time into small segments and writes the operator as a product of these small segments. And then one writes the Hamiltonian. If you want to simulate it on a circuit, we write the Hamiltonian as a sum of unitaries, and then take basically the time evolution operator for a single time slice and expands the time evolution operator in a Taylor series, reaching eventually a sum of I guess what we call a linear combination of unitary operators. This is what happens when you just expand the unitary evolution. And once you get, so for example, in the sum that is, I guess, on the right-hand side of the big equation on my slide there, then we have a coefficient which is a product of some alphas, which are the coefficients of the Hamiltonian, times a product of unitaries that basically constitute the Hamiltonian. And I guess in this case, one uses this very powerful lemma called the LCU lemma that tells us that if we have a unitary that is a linear combination of unitaries, you can write a very clever algorithm that basically can perform this this entire unitary using controlled action of those small unitaries. And this is a very powerful algorithm, which I will actually use in the algorithm that I will be discussing right away. But the point is that, you know, we are living in a world where the quantum computers are not very, I guess, well, they're not fault tolerant. And so it's important that we come up with approaches that are very resource lean, or the most efficient methods possible. And so the question is, of course, if we come up with something like that, it will, or better, algorithms that are better and better, then we will be able to simulate actual systems and maybe larger systems, and even demonstrate quantum advantage. And so this is why we're thinking about doing something better than the current state of the art. And what I'm going to present to you is basically a different approach to applying the time evolution operator by decomposing the Hamiltonian in some somewhat different way. And this is where it gets a little technical, and I hope that's okay with everyone. And so what we do here is we expand the Hamiltonian not in a Taylor series, but in an off-diagonal series expansion, which was an expansion that was devised in the context of quantum Monte Carlo a few years ago. In this case, what we do is first we choose a representation for a Hamiltonian. So we choose a basis that is identified here as a set of basis state Z. And we then write the Hamiltonian as a sum of what we call generalized permutation operators. A generalized permutation operator is basically, I guess I try to give a figure for that, is writing a matrix as a sum of not really permutation operators, but matrices that have at most one non-zero element in each row and column. And actually, this generalized permutation operator can be written as a product of a diagonal operator times an actual permutation operator, where permutation is basically you have a single one in each row and each column. So this is how you do that. And I should say, even though it may not be clear or very trivial, that it's always easy to do that. And there is a very simple technique of doing so. So once we have that, and we have the Hamiltonian as a product of diagonal operators, which can be non-local, and the permutation operator, so basically pairs and the sum of these products, then one of these permutations, for example, will generally be the identity, which means that the D, or the diagonal in front of this identity, is the classical Hamiltonian, or the diagonal part of the Hamiltonian. And the rest are basically off-diagonal permutation operators. When they act on a basis state Z, they give us another basis state Z prime. And we can always find, I guess, a representation where all the PJs other than P0, which is the identity, have no fixed point. So whenever a permutation operator acts on a Z, on a basis state, it gives you a different basis state Z, Z prime. It doesn't give you the same. So if, for example, you look at spin models, then the permutation operators are very simple. They are the Pauli X's, X1, X2, X1, X2, whatever is in the Hamiltonian that is proportional to Pauli X's is in there. And if you see a product of Z's, for example, that would be the diagonal part. And this will be the D0, for example. So it's a very easy thing to do. And I guess I gave here a few examples. Maybe I'll For example, if you look at the Hamiltonian, which is look at the second line in this is in here, you have sum of Jij Zij plus Jij with a tilde Zixj, then D0 is this entire non-local sum of Jij Zij, because you can imagine there's a P0, the identity in front of it. This is D0. And the various DJs is whatever is in front of the XJ. So all the Ds are very non-local. And the number of terms to which you decompose the Hamiltonian is very important for the complexity of the simulation, because it really sets the tone for what the complexity of the algorithm is. So the fewer terms you have, the better you are moving forward. So for those of you who are familiar with, I guess, existing algorithms, then this is a very, I guess the number of operators here are there's very few of them, I would say. So what do we do with this decomposition of the time evolution operator? We actually start with a Taylor expansion of this exponent, and we write basically Taylor expanding this e to the minus iht, so you get minus it to the n divided by n factorial times h to the n, but we know we wrote h as a sum of terms, and if we expand this parenthesis, we actually raise it to the power of n, what we end up with is a sum of some factor negative it to the n divided by n factorial times a sum of all possible products of length n of either d0 or djpj. And basically, this is basically like a binomial expansion. You just raise a sum of terms to the power n. This is everything there is to it. And if you take one such term, this is just an example. You have all the possible terms you can think of. But for example, if you take one such term, it could be d0, d0, d1, p1, d0, d1, p1, d0, d0, d2, p2 times d0. This is just an example. But the reason I give this example is because it's interesting to see what happens when this operator acts on a basis state z. So for example, you can start with d0 acting on the z, and what it does, it actually pulls out a number, because it's a diagonal operator, and this number, the way that I will call E of z, it's basically like the classical energy of z, because d0 is the classical portion of the Hamiltonian. So you can eliminate d0 and end up with a factor outside, and then you have this p2 acting on a z, but p2 changes z to some z prime. So we know what p2 does, and then d2 comes and acts on z prime. And what it does, because it's diagonal and it's acting on a basis state, it pulls out some factor, a number, d2 of z prime. And you can actually go on and act with d0 and z prime and so forth. And actually what you end up with, all the d's can be completely removed or pulled out of this action of this term on this basis state. So you end up getting some number, which you can easily compute. The things that you can't pull out of this term are only the p's, for in our case, p1, p1, p2. This is what I would call the off-diagonal core of that term, which consists of unique products of permutation matrices. So if you look at one specific product of permutation matrices, you will have all of them. It's, I guess, instructive to think of this product when it acts, and there's Q of them for any term, there's a number of them. When this product acts on a Z, you can picture it as a walk on the hypercube of basis states. What do I mean by that? When we consider the action of this product on Z, on a basis state, you can consider Z as a vertex, and then the first P is a jump to some Z1 to another Z, and then Pi2 acts on a Z1, gives you a Z2, So basically, it's just a walk or a hop or a whatever you want to call it. You hop around on the hypercube of basis states, and each jump basically generates a sequence of classical energies, because from Z you get E of Z0, from Z1 you get E of Z1, and so forth. And also every jump, because every P1 is associated with, there is an associated D1, every every edge or every jump pulls out another number, di1 of zi1, di2 of z2, and so forth. I know it's a little technical, but this is what it is. And the key, I guess, of this method or this expansion is that you can think of all the terms, and there is an infinite number of them, that correspond to a one single particular off-diagonal core. So for example, in the example that I gave right now with P1, P1, P2 as a core, this is not so the term D0, D0, D1, etc. is not the only term whose core is P1, P1, P2. There's actually an infinite number of them, and each of them pulls out a different number. And the key to this method is that if you take a look at the sum of all the numbers that are pulled out from a single or for a single off-diagonal core, you can actually perform this sum analytically, ending up with what is known to be the divided difference of the function e to the minus it with respect to the energies over the vertices. It's just a generalization of e to the minus iit to the case where you have multiple inputs. That's the best thing, the best way I could describe divided difference. For those of you who are not familiar, it's kind of a generalization of what the function would be if it had several inputs. The important thing is that this sum here is this expression here, and you can calculate this expression very easily if you know what these energies are. And in our case, we know them. They are basically some diagonal energies, which we know how to compute for any physical Hamiltonian. So if you had that, you end up, when you act with the unitary on the basis state Z, you end up with a sum over all combinations of projects of PJ operators times some divided difference. This is a number that you can compute for every term. And these are the product of the D's that correspond to the P, to this product of P's. But you end up basically with a sum of terms that each term is easily calculable, which is a number, times a permutation operator acting on the original basis state. And okay, I'll just skip that. I was just saying that basically this entire e to the minus iht when it acts on a z is similar to this operator, which we call vz of t. Again, I just said what it was. It's just a linear combination of alphas, just numbers, and p's, product of permutation operators. We'll skip that. And if you know what I just told you, and you look at your e to the minus iht and you dissect it to smaller time slices, in our case, if you want to use this off-diagonal expansion and you want to act with it on every time slice independently, like you normally do, then the number of slices that you need is actually not proportional to time times the norm of the Hamiltonian, which is really usually always the case. All we need to do is actually set the number of times to be proportional to this dimensionless time factor, which is time times something that is actually smaller even than the off-diagonal norm, or basically the norm of the off-diagonal portion of the Hamiltonian. And why is that? It's because when you look at the time evolution operator, and I told you what happens when it acts on a single basis state, you can imagine what happens when you write U as acting on all the states, or basically a representation of the entire operator. So you act on the identity, and then you apply U on each and every basis state Z. The action of U on every Z is this VZ of Z, which I just told you what it was. You end up, to make a long story short, I know it's technical and I will not go into details. You end up basically with an off-diagonal part of the unitary, which has to do only with the off-diagonal part of the entire Hamiltonian, and everything that has to do with the diagonal portion of the dynamics is actually pulled out and can be very easily computed. Actually, the entire complexity lies in here. It's a sum of numbers times unitaries. But we know what to do when we have numbers times unitaries. There's a tiny bit of details in exactly what the unitaries are. They're basically just the permutation operators times some phases that are easy to construct. Again, I know for now you see a symbol that you don't recognize, and I don't blame you, but this is just to show that you can write the off-diagonal operator as a sum of easily computable coefficients times easily implementable unitaries, because these permutations, product of x's or whatever, are very easy to do a control permutation of, and these numbers are very easy to, the actual numbers are very easy to construct. So what we do is we follow, I guess, this Berry et al. Technique. We introduced to the world this powerful algorithm of LCU, linear combination of unitaries, that tell us that if we have a linear combination of unitaries, then we already have an algorithm to circuitize, to digitize this unitary. And to do that, we need to cut off the expansion order, and the cutoff is proportional to the logarithm. This comes from the LCU, and those of you who are familiar with LCU will recognize this term. It's the logarithm of the this dimensionless time. Normally, dimensionless time is the actual time of the evolution times the norm of the Hamiltonian, but in our case, it's not that, because we actually completely figure out what to do with the diagonal part. So you end up having to cut off the series with something that is proportional to the logarithm of only the norm of the off-diagonal part of the Hamiltonian. And for example, if it's small, it just means that you can do things very, very, with a circuit depth that is much, much shallower than what you would normally do with existing algorithms. I will not go into the details of how LCU works, because it's easy to read about it. And also, presumably, hopefully, most of you know what LCU is. You need to prepare state, which is easy to do. You need to write controlled unitaries that in our case are basically controlled phases times controlled permutations. They are all easy to come by. Okay, I will skip the details of how you do the controlled permutation, but believe me, it's not very difficult. And by the way, there's an archived version of this paper, which I neglected to put a link to, but I will maybe do so on the Slack channel. But anyway, you can read the details on the archive paper, and it's not very difficult to do. And anyway, what you end up with is an operation that requires O of Q ancilas, or generally it's O of Q times M, where M is the number of terms to which you decompose the Hamiltonian. And again, in our case, the number of terms is much, much lower than what you would do if you did, for example, the Taylor series expansion, Hamiltonian simulation, or any other algorithm for that matter. So you apply the LCU only on the off-diagonal part of the Hamiltonian evolution. You also have a diagonal part, which is really very easy to do because it's just a phase. It's e to the minus I delta t times the diagonal Hamiltonian, very easy to do. You execute this bit for r times, or r again is proportional to the off-diagonal norm. And at this point, you can look, for example, again, it's just an example of what happens if you compare a truncated Taylor series expansion Hamiltonian simulation to off-diagonal expansion. What you find, again, I mentioned it, both algorithms scale with respect to dimensionless time t, because the qubit count is proportional to q, and which is log t, and the gate count also. But and in our case, t is very different because it only counts, I guess. For example, let's take the lower table here. You have many terms, j, I, j, k, z, I, z, j, z, k, for example, and other z, I, z, j, x, k. And if you try to do a Taylor series expansion, you end up with 2n cubed terms. Whereas in off-diagonal expansion, you only end up with n terms because the decomposition is much more efficient. And if you look at the dimensionless time, again, then the norm here is much smaller than the norm of what you would get, or of the, because you're only looking at the norm, or actually something that is bounded from above by the norm of the off-diagonal part of the Hamiltonian. Whereas in Taylor series expansion, that's not the case. So I'll just finish and tell you that this algorithm is basically, we're hoping that many people would use it for systems where the diagonal part is dominant, and where and in this case you would get a lot of savings in qubits and gates, and we hope that people would use it in the NISQ era, obviously, and we have some experience going on with small systems. Obviously, there's only so much we can do, but definitely it does better than other schemes. I will mention that I would like to acknowledge funding from the US Department of Energy, Basic Energy Sciences. And I think I'll end here, and if there's a questions, I'm really happy to answer. So thank you.
Okay, thank you, Itay, for a very interesting talk. I think nobody dared ask any questions on the Slack yet, so I think I'll just shoot one question myself, which is, I found it very interesting, this decomposition scheme for the Hamiltonian. I was wondering, how difficult is it to perform this decomposition? I mean, is it system dependent? Are there any systems that are particularly complicated to decompose in this diagonal form plus all these terms?
Right. So I guess on the face of it, it's very, I guess maybe not very trivial to do. But if you take for any spin system or fermionic system or bosonic system, it's easy to do. If you take spin systems, such as an example, then the decomposition is basically just identify all the terms that are in front of xi, some Pauli x, and group them together. And maybe if there's an x2, you group all the terms that multiply x2, you group them together. If there's an x1, x2, you group all the terms that multiply x1 and x2 together. So to answer your question in short, it's really not complicated. It's actually, for spin systems, it's trivial, and it's not harder to do for bosonic or fermionic systems.
Okay, good. I have another question, which is, Have you considered the case in which your Hamiltonian depends on time?
That's an excellent question, and we are currently writing a paper about it.
Oh.
And it turns out that it's slightly more, well, I wouldn't say slightly, it's more complicated, but it's doable. And we hope to have a paper out on that as in the next, in the coming months, maybe 2 or 3 months.
Okay, thanks.
Okay, thank you, everyone. Thank you.
Okay, it seems that we are taking a bit to post questions on Slack, so I guess we can finish here.
Okay.
Thanks again,
yeah.
And see you around.
Thank you very much. Thank you. Bye-bye.
Bye-bye.